Radar, sweeping the surrounding sea, pinpointing ships, coastlines. Every sweep plotting a new situation. By combining this information with data on your own course and speed, it has long been possible to create a vector triangle, identifying any target's true speed and course. In busy shipping lanes with dozens of vessels sharing the same sea space, and some vessels travelling at high speeds, calculations need to be swift and accurate.
The word radar is believed to have been derived from the phrase radio detection and ranging. For many people, radar is difficult to understand. However, its principle is simple. Short radio waves, like acoustic waves, are reflected by objects that come in their way. In the radar, a short burst of electromagnetic energy is transmitted, hits an object, and then returns. Since the velocity of propagation is known, it's easy to calculate the distance to the object. As long as we are able to measure the time from which transmission is started until the echo returns. The transmitted pulse must be short in order to distinguish between echoes located close to each other. On board a ship, the radar has two main tasks. One is to function as an aid to prevent collisions. As with the help of radar, one can see in fog and darkness. The other is to assist navigation, particularly at landfalls and when navigating in coastal waters or in archipelagos. Radio waves are electromagnetic wave motions of the same kind as those of light, and consists, like all other wave motions, of a train of crests and troughs. This radar block diagram can be divided into 5 main parts: antenna, with motor, gear, etc., which directs and transmits radio waves; transmitter with magnetron, modulator and trigger, which generate radar waves; receiver with mixer, amplifier, equalizer and video amplifier, which receive the reflected waves; display unit, which measures the time and presents ranges and bearings in a suitable way for navigational purposes; power supply with power transformer, which provide power to the various radar parts. It is not necessary for the radar operator to know all the details about each radar component. However, for safe and efficient use of the radar, a basic understanding of how a radar works, its compatibilities and limitations, is a minimum requirement for all navigators using radar in their work. The pulse repetition frequency is defined as the number of pulses transmitted per second. Long pulse equals low PRF, while short pulse equals high PRF. Long pulse means more power and longer radar range, but less resolution in range. Short pulse means weaker pulse, less radar range, but better resolution in range. Selection of pulse length may affect the radar range resolution in a negative way. This is the situation as seen on a ship sailing in a narrow channel, as seen on X-band radar operating on short pulse. This is the same situation as displayed on S-band radar operating on long pulse. Observe that the channel is closed in front of the ship. This is the situation on a ship entering a harbour, as seen on an X-band radar operating on short pulse. This is the situation on a ship entering a harbour, as seen on an S-band radar, operating on long pulse. Observe the big difference in ability to display details between the two radar types. Marine radars transmit energy of varying strength in form of short pulses or bursts. Pulsed power can produce biological changes not obtained with constant wave transmissions. At a short distance, transmissions from marine radars may pose a health hazard. Follow the instructions from the radar manufacturer closely and don't take any chances. When working close to a radar antenna, make sure that a warning sign has been placed on the radar console, clearly telling everybody that no startup should be attempted before the work in the antenna is completed or cancelled. Two radar terms are often mixed or used incorrectly, namely radar scan and radar sweep. Remember this: a radar sweep is the transmission of one radar pulse only. A radar scan is one complete 360 degrees rotation of the antenna. During one scan, normally several thousand sweeps are generated and transmitted. In modern radar systems, both sweep and scan correlation may be used to filter away unwanted noise. Read the manufacturer's manual and do not mix the terms sweep and scan, as this can produce unwanted effects on the radar screen. Range discrimination is the ability of the radar to discriminate between two small objects close together in the same bearing. That is, display separate echoes. The further object must not be in the shadow of the nearer one. The most important parameters affecting range discrimination: selected pulse length, the size of the spot. If possible, short pulse and short range should be selected, and focus and brightness carefully adjusted. This animation tries to illustrate what may happen when two ships are close in range and the radar is operated on short pulse. On the radar screen, two echoes can be seen. As long as the ship at the longest range is not in the radar shadow of the nearer one. This animation shows the same situation, but the radar is operated on long pulse. On the radar screen, only one echo is visible. Bearing discrimination is the ability of the radar to discriminate between two small objects close together, at the same range, but with different bearings. That is, the ability to produce two separate echoes on the radar screen. The bearing discrimination depends on the horizontal beam width of the antenna, the spot size. Correct focusing and brightness settings will improve the bearing discrimination. This picture tries to illustrate what may happen when two ships are close in bearing and the X-band radar with a narrow horizontal beam width is used. Two echoes can be seen on the radar, as long as the two ships are not hit within the same beam. This picture tries to illustrate what may happen when the same beam hits two ships. Only one echo is displayed on the radar screen. The radar's possibility to reproduce an area or a ship correctly and to discriminate between close-lying targets is limited and varies with different types of radar. The discriminating ability in range is usually 25 to 75 metres. However, the accuracy is lower on long ranges. The discriminating ability, laterally, is usually 1 to 2 degrees. Radar sets with a wavelength of 3 centimetres have, generally speaking, a better discriminating ability compared with a 10 centimetre wavelength. We have normal transmission of radar waves when conditions are such that the radar range is approximately 10 to 15% greater than the distance to the optical horizon. Generally, one can say that normal conditions exist in areas with cold air masses. Generally speaking, the longer the wavelength, the greater is the tendency to bend round objects. Hence, you can expect the 10 centimetre radar to have a greater range than the 3 centimetre radar.